Satellites are fascinating machines that orbit our planet for years without falling back to Earth. But how do they do it? The secret lies in the delicate balance of physics, particularly gravity and velocity. When a satellite is launched, it reaches a specific speed known as orbital velocity. This speed is crucial. It allows the satellite to counteract the pull of Earth's gravity. For example, a satellite in low Earth orbit, like the International Space Station, travels at about 17,500 miles per hour. At this speed, the satellite is moving fast enough that as it falls toward Earth due to gravity, the curve of its path matches the curvature of the planet. Essentially, it's in a constant state of free fall, but because it's moving forward so quickly, it keeps missing Earth. This is what creates the sensation of weightlessness for astronauts aboard. Now, let's talk about altitude. Different satellites operate at various altitudes, and this affects their orbital speed. A satellite in geostationary orbit, for instance, is positioned about 22 to 236 miles above the equator. Here, it moves at a slower speed compared to low Earth orbit satellites, but it matches the rotation of the Earth. This means it appears to stay in the same spot in the sky, which is perfect for communication satellites. However, satellites don't just float indefinitely. Over time, they can lose altitude due to atmospheric drag. Even at high altitudes, there are trace amounts of atmosphere that create friction, gradually slowing the satellite down. When this happens, it can spiral closer to Earth, eventually leading to re-entry. But satellites are designed with this in mind. Many have onboard thrusters that allow them to perform adjustments, known as station-keeping maneuvers. These corrections help maintain their orbits and counteract the effects of drag. For instance, if a satellite starts to drift, it can fire its thrusters to boost itself back to the correct altitude and speed. Long-term stability is also a key factor. Satellites are built to withstand the harsh conditions of space, including radiation and micrometeoroids. Engineers carefully calculate their trajectories and design them to last for years, ensuring they can continue to function effectively. In conclusion, the dance of satellites around Earth is a remarkable interplay of speed, gravity, and engineering. They don't just float, they are in a constant battle against gravity, using velocity and adjustments to stay in their designated paths. This intricate balance allows them to provide invaluable services, from weather forecasting to global communications, all while gracefully orbiting our planet.